All right, hi guys. Welcome. I'm going to be doing a video for the final exam review. This one's real long, so it's going to take me a few videos. Right now I'm going to try and get through as much as I can. Let's just see how it goes. So this is covering units 1, 2, 3, 4, 5, and 6. So it is a lot of questions. Again, this is a review. You don't have to do it, but I highly suggest that you do. I think it will be helpful for you. And at the end of the year, you can also come back to this video, and this will definitely help you for the region. All right, so let's get started. I'm gonna go a little faster than usual, or at least I'm gonna try. And if I'm going too fast on YouTube, you can just slow down the pace. Okay. So if you need to do that, you go ahead. Anyways, let's get started. Number one, which unit is used to express an amount of thermal energy? Let's get my pen. So thermal energy, this is talking about heat, okay? And heat is a form of energy. We're gonna measure energy using the joule. Grams is for mass, mole is a quantity of a substance, and Pascal is like PA or kPa. This is pressure. So we're gonna wanna go with choice C, the joule. Okay. Let me just get rid of all this. All right, number two, they basically want us to determine what the correct reading would be on this thermometer. So we can see here, we're going from 0, we're going to 10, 20, and then each of these markings is worth basically 1 unit. So this one right here, this is like 5, 6, 7, 8, 9, and 10, so on and so forth. So we're going by ones, okay? And we are right here. Okay, we're like in between these two values. So this is 0 right here. This is 1, 2, 3, 4. So we are in between 4 and 5. So we know it's definitely not 0.3. And we also know it's not 4. We also know it's not exactly 5. So we're only left with one option. And again, remember that when you're reporting a value, the last digit should always be the digit that is in doubt. We're not actually sure that it's 4.3. It could really be 4.4, 4.5. We're not really sure. All right. Okie dokes. Moving on. All right, number three, during a laboratory experiment, a sample of aluminum is found to have a mass of 12.50 grams and a volume of 4.6 milliliters. What is the density of this sample expressed to the correct number of sig figs? So first you have to know what equation to use. This one is on table T, the very last page of your reference table. And again, our formula for density is D equals M over V. So we are going to divide our mass by our volume. So that's 12.50 divided by 4.6. And when we do this on the calculator, y'all can pause the video and try yourselves. All right, I got a very long number. Let me write it over here, 2.71739, and this keeps on going. Now they say to report to the proper number of sig figs. So remember, when you're dividing and when you're multiplying, you report your value to the lowest amount or the limiting amount of sig figs. So this number here is 4 sig figs. This one has 2. So that means that this bottom one is limiting how accurate or precise, how precise our answer can be. Okay, so we have to report our final value to only 2 sig figs. So we're going to focus on these two. Our final thing that we should really be looking at is the 7. Do we keep it as a 7 or should we round up to 8? The number preceding it is a 1. So we're going to keep it at 7. So our final answer should be 2.7. All right. Alrighty, number 4. So which sample of matter has the greatest distance between the molecules at STP? So the things with the greatest amount of distance are the gases, which we have a great example actually right here. So gases look like this, essentially. Okay, there's lots of distance between their particles. So we're going to want to go with the thing that is representing a gas. So we're going to go with A. This little G right next to our little molecule is representing that it is in the gas phase. L is liquid, AQ is aqueous, means that it is in solution with water or mixed with water, and S is solid. All right, number 5. The solid object shown below has a mass of 162.2 grams. What is the density of the object? The correct number of sig figs. So they're making it a little bit difficult for us because they're not just outright giving us the volume. You have to calculate it yourself. This is a rectangular prism. So to find the volume of a rectangular prism, you do length times width times height. So we're just doing 6.0 times 3.0 times 2.0. This should be 36.0, okay? Bear with me one second, sorry. Alrighty, so this is our volume. And again, this is density, so it's D equals M over V. And they gave us our mass, so it is gonna ultimately, oops, where'd my pen go? Okay. All right, so I'm just gonna do it here. 162.2 divided by 36. All right. Now the thing is that this is being limited to only 2 sig figs. Okay, the 36 is limiting us to 2 sig figs. 162.2 has 4, but when you divide, you go by the thing that has the least amount of sig figs. So when we divide this, I'm just doing that right now on my calculator. Okay, I got 4.50555. So this just keeps repeating, so I'm just rounding it. But this needs to be rounded to 2 sig figs, so we're gonna focus on these two numbers. Do I keep the 5 as 5, or do I round it up to 6? I'm gonna leave it as 5 because the number right before it, preceding it, is a 0. So we're gonna want to go with choice C. All right. I need Jeopardy music for when I'm erasing. Okay. Number 6, in a laboratory activity, the density of a sample of vanadium is determined to be 6.9 grams per centimeters cubed at room temperature. What is the percent error for the determined value? So the first thing is that they are giving us, in a lab activity, this value is determined. So this is our measured value, but we need to know what is the actual value. Where would you go and get that? You got to go to table S. So we're looking at density. So we're going to go down to table S. Let me flip this. Vanadium is 23 right here, and its density, let me highlight this row. Where is density? Oy. Okay, density is 6.0 grams per centimeters cubed. Okay, so that's the accepted value. All right, and I'm just gonna scroll up a little bit so that I have room to write. So we do our measured minus accepted over accepted. And then because we were trying to get a percent, we multiply the whole thing by 100. We can also take the absolute value of the whole thing, okay? So our measured, this is what was done in the lab, is 6.9, but the actual value is 6.0. So I'm just plugging everything in, and then I'm multiplying by 100. Let me see what I get on my calculator. And I am getting 15%, okay? When you subtract this and then you divide by 6, you really get 0.15. But again, this shouldn't be in decimals. It's got to be a percent. So you multiply by 100, and that's how we got the 15%. So we're going to go with choice D. All right, cue the Jeopardy music. All right. Number 7. At STP, a 50-gram sample of liquid water and a 100-gram sample of liquid water have the same or different what? So they're both at STP. So they both have the same temperature. So this doesn't make sense. They have the same formulas. They're both H2O. They're not going to have the same volume because there is a different amount. So a different amount, a larger amount would obviously take up a larger volume. They are going to have the same properties because they are the same thing. One sample is just 50 grams and the other is 100 grams. Mass is a physical property. So the only thing that's actually different about them is their mass is different. All right, their volume is also different, but yeah. Okay, so they would have the same chemical properties because they are the same thing. Number 8, which particle model diagram represents xenon at STP? Xenon is one of our noble gases. Okay, so we're looking for a gas. So it's not C. That looks like a solid. And D, that also either looks like a solid or, I don't know, maybe a liquid. But it's definitely not C or D, okay? Gases always have lots of space in between them. So it would look either like something like A or something like B. Now, the problem is, how do I know what xenon looks like, right? Again, xenon is a noble gas. And at this point, we know that noble gases don't bond with anything. So they are monatomic, okay? They are not diatomic like this represents. That is not what they are, okay? These are going to be monatomic. They're always going to be floating around by themselves. So we're going to want to go with choice A. All right. Moving on to the next page, number 9, which statement describes a chemical property of silicon? Remember that a chemical property is something that describes how a substance will react with something else, okay? So choice A, B, and C, color, phase of matter, and melting point, those are all physical properties. This is the only chemical property here. This is, again, describing how something will react with something else. This is a chemical property. Number 10, which sample of carbon dioxide has a definite shape and a definite volume? The only sorts of things that have both definite shape and volume are solids. So you just got to go for the solid. Number 11, particles are arranged in a crystal structure in a sample of what? So something is arranged in a crystal structure. This is, again, describing a solid. So go with the solid. Number 12, which substance cannot be broken down by a chemical change? The only things that can't be broken down by chemical changes are elements. Okay. We should at this point be able to recognize that silicon is the element here. All right. Number 13, which phase change is an exothermic process? Exothermic, exo like exit. So this is meaning that energy is being released or heat is being released. So let's look at our options. So here, I'm not even looking at what the stuff is. I'm just looking at the phases. So we're going from solid to gas. In order to go from solid to gas, you got to heat it up. That means that something has to absorb. So not C, not A. Choice C, we're going from solid to liquid. This is melting. Melting and trying to melt something that requires heat as well. So that's endo. Doesn't make sense. Going from gas to liquid, this is condensation. In order to condense something, you have to remove the energy from it. So you have to release the energy. So we're going to want to go with choice B. But just to make sure, let's look at choice D as well. In choice D, we're going from liquid to gas. That is evaporation. In order to evaporate something, you got to heat it up. So that would be endo as well. So you want to go with choice B ultimately. All righty. Number 12. Am I looking at? No, I already did number 12. I'm going backwards. Okay, number 14. My bad. All right, number 14. Which grouping of the 3 phases of bromine is listed in order from left to right for increasing distance between bromine molecules? So we're going to want to go with choice D. Okay, I'll draw it over here. So choice D, we're starting at a solid. Then we're going to a liquid. Liquid would look probably something like this. And then a gas would look like this. Again, we want to see increasing distance between bromine molecules. So here in a solid, they're right up next to each other. They're very tightly packed. In a liquid, they're a little bit more spread out. And then in a gas, they're very far apart. Okay. All right. Number 15. Which substance has vibrating particles in regular fixed positions? This is describing a solid. Okay. Again, solids are basically fixed in their positions. They're stuck there. They want to move, but they're stuck in their position. So they just vibrate back and forth a little bit. Remember that everything moves. So we're going to want to go with A. This is the solid. Number 16, solid zinc chloride and liquid zinc chloride. So we got solid and liquid, but they're the same chemical. They're the same compound. We want to know what is different about them. The only thing that's going to be different about them is their physical properties because their physical states of matter are different. Alrighty. 17, which quantity is equal to 50 kilojoules? So we're basically trying to convert from kilojoules to just joules, okay? So again, you can remember the King Henry died unexpectedly drinking chocolate milk thing, and you can use that. Or you can just think of the words, okay? Kilo, we know that this means 1,000, okay? So that means that 1 kilojoule is equal to 1,000 joules, but I don't have just 1 kilojoule. I've got 50. So that's 50 times 1,000. That is 50,000. But the problem is that these 2 of them are reported in scientific notation. So it's not A, definitely not B. Okay. So let's see what how we would write 50,000 in scientific notation. Again, our decimal is really there. Move it 1, 2, 3, 4 over. So it's 5 times 10 to the 4th power. So we're going to want to go with choice D. Again, if I'm going too fast, just slow down the video, the speed of the video. You can put it down to like 0.75 speed or 0.5, whatever works for you. All right, number 18, which equation represents a physical change? So again, a physical change means that nothing is actually, we're not making a new chemical, okay? So I'm looking at A, and I can see that I'm starting with water, and I'm also ending with water, and the phases are different. I'm going from solid to liquid, And I can see here, this is kilojoules, 6 kilojoules, about 6 kilojoules. This is heat. Okay, so heat or energy is being added or absorbed by the water, by the ice, and it's being melted into liquid water. So we're going to go with A. And you can also take a look at all the other options. And you can see that you are making new compounds, you have different substances, new substances on the product side in each of these options. So you're going to want to go with choice A. Number 19, which form of energy is transferred when an ice cube at 0 degrees is placed in a beaker of water at 50 degrees Celsius? So this is basically heat. Okay, so we're going to want to go with thermal energy. Number 20. Okay, a cube of iron at 20 degrees Celsius is placed in contact with a cube of copper at 60 degrees Celsius. Which statement describes the initial flow of heat between the cubes? So remember that when two things are not at the same temperature, heat will flow from the thing with high temperature to the thing of low temperature. So the heat is going to go from the copper into the iron. So we are going to want to go with choice, let's see, choice A. Heat flows from the copper to the iron, again, from high temperature to low temperature. And heat will stop being transferred once the iron and the copper are at the same temperature. This will be at equilibrium. Moving forward, 21, which type of energy is associated with a random motion of particles in a sample of gas? We just went over this one. This is related to the heat. This is the thermal energy. Number 22, which temperature represents the highest average kinetic energy? When you see the word average kinetic energy, average KE is a measure of the temperature. So problem with the options is that they're not in the same unit. Okay, they're not in the same temperature scale. So you can do one of two things. You can convert everything to Celsius, or you can convert everything to Kelvin. In order to go from Celsius to Kelvin, that's what I'm going to do. I'm just going to add 273 to both of these. Okay, so this 27 plus 273 would be, this is 300 Kelvin. And 12 degrees plus 273 would be 285 Kelvin. So we can clearly see that choice C is the highest one with 300 Kelvin. Number 23, the temperature, we literally just did this. The temperature of a substance is a measure of the average kinetic energy. This is a definition problem, okay? Moving on, I think we're already on the third page. Going on to the third page already. Alrighty. 26, cooling curve problem. Okay, the cooling curve below represents the uniform cooling of a substance starting at a temperature above its boiling point. During which time interval does the substance exist as both a liquid and a solid? Remember that the only parts of a cooling curve that are going to have two phases present will be the ones that are horizontal. These are the phase changes, okay? So this is a cooling curve. This means that we're starting at gas, this is liquid, and this is solid. So at what point will we have a liquid and a solid? That is right here, right in between the liquid and solid. So right here, we are trying to freeze this liquid into a solid, okay? So this interval is between 7 and 9 minutes, okay? So that is what we should go with for our final answer. And again, that section was the freezing section. And if you were going the opposite way, if this was a heating curve, that would be the melting. All right. A sample of helium gas is in a sealed and rigid container. What occurs as the temperature of the sample is increased? So temperature is directly related to the speed of the particles, okay? So this means that things are going to start kind of colliding into each other more frequently. Okay, you heat stuff up, stuff starts to move faster. The faster it moves, the more likely that there are going to be collisions. So the frequency or the amount of collisions happening per second increases. So we're going to want to go with choice D. I just want to look at the other options though, just to explain why we would eliminate them. The first thing that they say is that this gas is in a sealed container. This means that we're not actually changing the amount of stuff that we have. So the mass isn't changing and the number of moles also isn't changing. C doesn't make any sense because temperature and volume are directly related, okay? Kelvin temperature and the volume of a gas are directly related. So if we were increasing the temperature of something, the volume would also increase. It would not decrease. So C doesn't make any sense. All right. Moving on, number 28. Base your answer to the following question on the information below. Which gas contains molecules with the highest average kinetic energy? again, average kinetic energy is just the temperature. So all you got to do is look for the thing with the highest temperature, and we can see that that is this. So that would be gas D. All right, number 29. Which phase change is accompanied by the release of heat? Release of heat means exothermic. So we did a problem like this before. So we're looking for the exothermic phase change, okay? Just a hint. I wish I had a little bit more room over here. But if you go from solid to liquid to gas, all of these things require heat to be absorbed. So going in this direction, everything is endothermic. If you go the opposite direction, if you go from gas to liquid to solid or any of these changes, these are all of the exothermic changes. So right here, solid to gas, okay, that is sublimation. And again, that's moving in this direction. That is endo. Liquid to gas, that is also endo. That doesn't count. Solid to liquid, that's melting. That also doesn't count. Liquid to solid, that's the only one going in this direction. So this is kind of like going backwards. So to take liquid water and to turn it into solid ice, you don't want to add heat to the liquid. That would make it a gas. You want to go the opposite way. You want to take away the heat. So you got to release the heat. This is exothermic. Okay, number 30. A gas changes directly to a solid. This is the opposite of what we just saw here. So gas to solid is deposition. Again, the way that I recommend memorizing these two, these are the weird ones. These are the two phase changes that skip directly over the liquid phase. The way I remember it is that solid, there's only two of them that work like this. So there's solid to gas. This one starts with S. So this one is sublimation. And then I just remember that the other one is deposition, going the opposite way, gas to solid. All right. We are moving along, y'all. We're moving along. Okie dokes. Oh, also shouting out period 5 and 9 because they asked for a shout out in my video. So, hey guys, how's it going? All right, number 31. At which temperature and pressure will a sample of neon gas behave most like an ideal gas? Remember that the conditions for an ideal gas are high temperature, low pressure, high T, low P. So you want to go for the combination that has the highest temperature but the lowest pressure. So I know it's definitely not A and B, okay, because 500K beats 300K. Now it's between C and D. We want to go with the highest temperature that also has the lowest pressure. So 2 atm is the lower pressure here. All right, and we literally we just said this. So under which conditions of pressure and temperature is a real gas most like an ideal gas? Again, high pressure, high temperature, and low pressure. So we're looking for high temperature. That's right here or right here. So I know I can get rid of A and C. And then I also want low pressure. So I'm going to go with choice B. Alrighty. Number 33. A sample of a gas in a rigid cylinder with a movable piston has a volume of 11.2 liters at STP. What is the volume of this gas at 202.6 kPa and 300K? Now, one thing that I'm going to say is just make sure that when they give you a question like this is a combined gas law problem. Let me write this over here. So this is the combined gas law. When they give you something in STP, okay, they're going to give you the pressure in some value. It can be either kPa or it can be atm. If they give you something in kPa, make sure that when you're using the STP values, you go with the pressure that is matching this. So we're going to want to go with the kPa value for pressure, okay? So again, that is P1 V1 over T1. This does not need to be memorized. This is in table T. This is in the equation section of your reference table. So I'm just going to go ahead and I'm going to plug everything in. So my initial pressure, again, is STP. So initial pressure in STP is 101.3 kPa. And I'm just going to avoid units for right now because it's just going to get too messy. And they're telling me that my initial volume is 11.2. So I'm going to just plug this in. So 11.2. And my initial temperature is T. Is standard temperature. Sorry. And that is 273K. Remember when you're dealing with the gas laws, all your temperatures have to be in Kelvin, okay? Because the relationships are based on the Kelvin temperature. So that is 273K. And then we want to know what is the volume. So we don't know what V is. You can leave it as V2, but if it makes you more comfortable to solve this, you can just write X. We don't know what X is. That's representing the second volume, the final volume. We know that our new pressure is 202.6. So I'm going to replace this with 202.6. And my new temperature, we've raised our temperature. We've gone from 273K over to 300K. And again, we want to know what happens to the volume. So what we're going to do is we are going to simplify the top. Okay, so I'm going to do 101.3 times, what am I doing? 11.2. And again, you can pause this video, you could do it yourself and then check back and see if you got it right. When I multiply this, I got 1,134.56. And when we combine this is just 202.6x. And now you just go ahead and you cross multiply. I'm going to do that right now on my calculator. And what did I get? I got 6.15. And again, they're asking us for the volume, so it's going to be in liters. So we're going to go with choice B. All right. Next question. I love these questions on the region because they're like giveaway questions. Please don't get these ones wrong, right? This is really talking about Avogadro's law, Avogadro's hypothesis, okay? Which sample at STP has the same number of atoms as 18 liters of neon gas at STP? It doesn't matter what gas you're comparing it to. It doesn't have to be the same gas. Any two gases at the same volume, temperature, and pressure will also have the same number of molecules. And it is really important that you remember that this has to do with molecules, not atoms, okay? Not atoms, it is molecules. All right, because for example, if you had let's say you had 10 atoms of neon gas. Neon is always monatomic. So, or let me use a smaller number, 3. We've got 3 atoms of neon. Okay, but let's say we have 3 molecules of carbon dioxide. Carbon dioxide has 3 molecules, 3 atoms in each one. So this wouldn't make sense, okay? If we've got three, like think of it as pieces, 3 pieces of neon gas, there's only 3 atoms. But if you've got 3 molecules of carbon dioxide, that's 1, 2, 3, 4, 5, 6, 7, 8, 9 atoms. So it doesn't go by atoms, it goes by total number of molecules, all right? So all you got to do is just match up, make sure if it's a molecules question, that matches, okay? Sometimes they ask, is it the same number of atoms or the same number of molecules? Go with molecules. So we just want to match up our unit. So we're just looking for something that says 18 liters. So there we go. That's it. Just match that up. All right. Make sure your units match. All righty. Okay. Moving forward. All right. I'm also just noticing that this right here is specifically saying the same number of atoms. Okay. So if they are saying atoms, just make sure that, the unit, whatever unit that they're giving you, that you match that up. All right. Okay. Number 35. I think, I'll try and do this page. Maybe I'll stop there. Maybe I'll do another. I'll see how I'm doing. Alrighty. Number 35. Which phrase describes the motion and attractive forces of ideal gas particles? Okay, so this is where I remember when we were doing this, I asked you guys to like circle or highlight this entire slide to know all the points, all the things that describe an ideal gas. Okay, they are important to know. So ideal gases, do they move in random straight lines? Yes, they do not move in curved lines. Okay, they don't do this. They move like this in random straight lines. So it's definitely not C or D. Also, ideal gases have absolutely no attractive forces between them. So definitely not B. We're going to want to go with A. Number 36. Under which conditions of temperature and pressure does a sample of neon behave most like an ideal gas? Again, we did this one before. High T, low P, high temperature, low pressure. So highest temperature match with the lowest pressure possible. Okay. So I'm going to cross off A and B. Those 100 doesn't compare to 400K. And between 400K, between C and D, we want to look which one has the lowest pressure. So that would be choice C. 0.25 atmospheres, very low pressure. 25 atmospheres is very, very high pressure. Alrighty. Get rid of all this stuff. Number 37. A real gas differs from an ideal gas because the molecules of a real gas, so they behave obviously different from an ideal gas. They have some volume, okay? An ideal gas has no volume, and they also have no attraction for each other. So this would be the opposite in a real gas. A real gas does actually have some volume, and they actually do have some attraction for each other. So we would want to go with choice B. All right. Okay, so this is exactly what I was talking about in that other question. So compared to a 1 liter sample of carbon dioxide in a sealed rigid container at STP, a 1 liter sample of methane, that's methane, in a sealed rigid container at STP has the same, so they're at the same temperature. They're at the same temperature, pressure, and they're both 1 liter, so that's volume. So they're at the same temperature, pressure, and volume. They are going to have the same number of molecules. And this is why this wording is so important, because if you draw out what CO2 looks like, again, CO2 has 3 molecules, CH4 has 5, okay? But there are going to be, all right, if you had the same number of molecules, this is going to be the same number of molecules, okay? So this is 1 molecule of carbon dioxide. This is 1 molecule of CH4, but you can clearly see that the number of atoms are different, okay? CO2 has only 3 atoms. Methane has 5 atoms. So make sure that you're being really careful, okay? The correct word that you want to go with is molecules. There is a difference. All right. I'm glad this question came up so that we could actually see what we were talking about before. Okay, another practice problem. Again, this one is the giveaway. Okay, at STP, which sample contains the same number of molecules as 3 liters of H2? So you just want to go with this thing that has the same volume. So 3 liters. All right, number 40, which set of values represents standard pressure and standard temperature? Where do you go if you don't remember it? And again, you don't have to memorize this at all. Actually, memorizing it is a waste of time, in my opinion, because it is literally right here. So try not to memorize stuff that is on the reference table, because you're kind of like, you're wasting good brain power that could be being used for something else, like understanding a concept, okay? So standard pressure can be one of 2 things, because everything is given in 2 units. So you can have 101.3 kPa, or it could be 1 atm. Standard temperature can be given in Kelvin or Celsius. In Kelvin, it's 273 Kelvin, and in Celsius, it is just 0 Celsius. So we just want to find the thing that matches, okay? So the first choice doesn't work because 101.3 is supposed to be kPa, not K. That doesn't work. 1 kPa, that doesn't work. It should be 1 atm. 101.3 kPa in 0 degrees Celsius. This is a good match. D doesn't work because 101.3 should be kPa and 273 should be Kelvin. All right, so choice C. All right. Number 41, we've already done a combined gas law, so I'm not going to solve this one. I'm just gonna set it up real quick, and then I will just tell you guys what the final answer is. Okay. So I need more room. Wish I had more room. Okay, you know what? Yeah, I'll do this. I'll write it like on the side over here. Alrighty. So 220 ml. You know what? Bear with me, guys. I'm gonna write this out first. Type away. Okay, so 220, that's my initial volume. That's here. Is in a cylinder with a movable piston at 105 kPa. That is my pressure, and 275 Kelvin. The piston is pushed in until the sample has a volume of 95 ml. So that's my new volume. The new temperature of the gas is 310. And what is the new pressure? So you guys solve this and you should get choice D, 274 kPa. Again, we already did an example of this, so just use what we did in the other one to help you solve this one. Alrighty, number 42. Which temperature change would cause a sample of an ideal gas to double in volume while the pressure is held constant? So if pressure is being held constant, we're looking at the relationship between volume and, oops, hey, where'd my pen go? Volume and temperature. And this is a direct relationship. So if you double the volume, you double the temperature. Or if you double the temperature, you double the volume. So we want to double. And again, when you're talking about the gases, the ideal gases, it is the Kelvin temperature. So C and D, ignore. We're not talking about Celsius, okay? We got to be in Kelvin. And we want to double everything, okay? So we want to double the volume. And in order to do that, you got to double the temperature. So we're going with B. A doesn't work because that is cutting it in half. So if you did this, you would decrease the volume, not increase it. All right. 43. Given the cooling curve of a substance, during which intervals is potential energy decreasing? Okie dokes. Sorry, I didn't even finish that. My mind is all over the place, y'all. So we want to find the spot where potential energy is decreasing and average kinetic energy is remaining the same. So again, average kinetic energy is the temperature. So you're looking at, there's two possible answers. This right here, BC and DE, are both spots where the temperature is not doing anything. This means that the average kinetic energy is not doing anything. So these are your two options. Also during this time, potential energy is changing. In a cooling curve, the potential energy is going down. Again, in a cooling curve, you're going from a gas to a liquid to a solid. So if you're going from a gas to a liquid or a liquid to a solid, you are giving these particles less room to move around. This means less potential energy. All right. So this is why potential energy goes down in a cooling curve. So we want to go with choice BC and DE. So we're going to go with choice C. Alrighty. The heat absorbed, number 44, the heat absorbed when ice melts can be measured in a unit called measuring heat. That is joule. Okay. Degrees is temperature. Temperature and heat are not the same thing. Torr is another unit for pressure, and mole is a measure of the quantity of a substance. All right. Number 45, as a 15.1 gram sample of a metal absorbs 48.75 joules of heat, its temperature increases 25 Kelvin. What is the specific heat capacity of the metal? Now, let's say that you get to the region or you get to the final exam, and for the life of you, you just don't remember what equation do I have to use. What you should do is start circling your numbers, okay? Look at your units and start figuring out what these things are, okay? I see 15.1 grams. This is M. This is mass. 48.75 joules, this is heat, that's Q. And 25K, that's temperature. And specific heat capacity, that's represented by C. There's only one equation that talks about all three of these things, and that's the specific heat equation, MC delta T. So now I'm just going to plug everything in, okay? They give me Q, that is 48.75. The mass is 15.1. We don't know what C is. You can write X if you prefer that. And its temperature overall increases by 25 Kelvin. So they've already given us the change. Okay. So all we got to do is just solve for C. So we're just going to simplify this side. Okay. So I'll write it down here. Actually, hold on a second. Let me write it up here. So 48.75 equals, and again, we're going to simplify. So I'm doing 15.1 times 25. That is 377.5 C or X. I'll just write X, okay? Now to get X by itself, you divide by 377.5. Okay, and honestly, you don't even need a calculator at this point because if you look at this, right, you have a small number divided by a larger number. This will give you a decimal, and there's only one option here that is a decimal, and that's A. All the others are too big. Okay, so you should get, when you divide these, you should get 0.129. Okie dokes. And also that kind of ties into this thing that I'm always trying to tell you guys, like make sure that your answers make sense. Okay. So if you were to go with like 7.74, that doesn't make sense because you had a small number divided by a larger number. You should get something that is lower than 1 or a decimal. All right. Next one. What is the amount of heat required to completely melt melting, melting, melting. This is another heat equation. This is the heat of fusion. Again, fusion is another way to say that something is melting. This is Q equals M H F. Okay. Again, you don't need to memorize what HF is. All right. It is on your reference table. I'll show you real quick right here. Here are the physical constants for water. Heat of fusion is 334 joules per gram. Again, what this means is that it takes 334 joules of energy or heat to melt 1 gram of water. Okay. And that value is different for every single substance. Okay. That is specifically just for water. Alrighty. So we just basically just plug everything in. So what is the amount of heat? That's Q. We're solving for Q. Our mass is 200 grams, and we just saw that our heat of fusion is 334. This comes out when you multiply them to 66,800 joules. So that is how much heat it takes to melt a 200-gram sample of ice or solid water. Alrighty, guys, I think I'll do one more page and then I am going to call it quits because down in a thirst here. Alrighty, so 47. Now we got a heating curve. All right, the graph below represents the relationship between temperature and time as heat is added to a sample of H2O. Alrighty, so which statement correctly describes the energy of the particles of the sample during interval BC? So that's talking about right here. Okay, again, this is a heating curve. So we're starting with solid, going to liquid, and this will eventually turn into a gas, but it's cut off in this graph. So we're going from solid to liquid. This is melting, okay? And also during a phase change, okay, you can see here, it's literally a flat line. Temperature is not doing anything. Temperature is also the average kinetic energy. So average kinetic energy does not change during a phase change. So we can eliminate A and B and also D, okay? Because they're saying average kinetic energy increases, increases, increases. That's not true, okay? It's staying the same. Also during this time, potential energy goes up. Okay, we're going from something that looks like this to something that looks kind of like this. Okay, we are giving this thing way more potential to move around. Liquids have more potential energy than solids do. So potential energy goes up and kinetic energy remains the same. All right. Another heating curve. Okay. This is actually literally a repeat of the last question. So we are given this diagram with a heating curve for some substance. We don't know what the substance is. It doesn't really matter. During which time interval is the average kinetic energy of the particles of the substance constant? So when is temperature staying the same? That's basically what they're saying. Okay, so it's staying here and here. That's where it's staying constant, and potential energy is going up in both of these, but they only give us one of these options. They only give us BC as an option. Okay. DE is literally not in the choices. So, alrighty. 49. Okay, this is another specific heat question. So again, we're using Q equals MC delta T. So solid aluminum has a specific heat capacity of 0.9 joules per gram Kelvin. How many joules of heat are absorbed to raise the temperature of 24 grams of aluminum from 300K to 50K? So we don't know what Q is. They're saying what is the heat, okay? They give us the mass. The mass is 24 grams. The specific heat capacity is 0.9. And the change in temperature, we're going from 300 to 350. Remember that delta T is really T2 minus T1, or the final temperature, which is this, minus the initial temperature, which is 300. So it's a positive change. It's positive 50, okay? So we take this, we multiply everything all together. I'm doing that right now. And I am getting 1,080. That's not necessarily an option, but what they are doing is they're using significant figures, okay? So they're reporting this to significant figures, so we would want to focus on these. So this is my last significant figure, 0. Do I keep it as 0 or do I push it up to 1? I'm going to want to push this up to 1 and round this, okay, basically to the nearest 100, because the number preceding it is larger than 5. So we're basically rounding this to 1100, right? So when you do some sort of calculation and you see that it's like kind of close to something, but it's not exactly, round it. They're reporting it to significant figures. So use your knowledge of sig figs. All right, 50. Okay, another heat equation question. So when 420 joules of heat, again, Q equals MC delta T, 420 joules of heat energy is added to 10 grams of water at 20 degrees Celsius. The final temperature of the water is what? Now remember that this equation can be expanded. So I'm going to actually erase that, and I'm going to specifically write T2 minus T1. All right. Now they're giving us heat. That's 420. That's Q. They're giving us the mass. That's 10 grams. We know the specific heat of water is 4.18. That is, again, on table B, physical constants of water. And now I have to figure this out. So the final temperature, that's T2. We don't know what it is. But we do know what the initial temperature was. That's 20. Okay. Now these two things are being attached to each other by subtraction. So we can't touch them yet. Okay. But I can simplify this part. So 10 times 41.8. I don't need a calculator for this. I just move my decimal over 1. So it's 41.8. And I want to get this out of this side. So I'm going to divide this whole thing by 41.8. Get rid of this. 41.8. All right, I'm going to do that on my calculator. 420 divided by 41.8. All right. And so what I'm going to do is I'm just going to erase this, simplify this. And I got about 10, guys. All right, so I'm just going to write 10. It's like 10.0, yada, 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 just rounding to 10. And now what I'm left with on this side is just T2 minus 20. And so how do I get T2 by itself? Well, all I got to do is just add 20 on both sides. Get rid of it. And I am left with T2 by itself, and T2 equals 30 degrees Celsius. So I'm going to go with choice B. Okay. Okay, number 51, another heat question, but not the heat equation, not the Q equals MCT. For this one, we are also looking at heat of fusion. Don't forget that there is another one, heat of vaporization. This is the amount of heat that it requires to boil something. Okay, I think I have a few questions like that on here. But again, Q equals M times HF. What is the total amount of heat required to completely melt? Again, this is fusion, 347 grams of ice. So 347 times the heat of fusion for water is 334. Just doing this on my calculator, and I got this exact value. Oops. Nope, that's not working. Sorry, y'all. Nope. Alrighty, I got it. So this is the exact value that I got. Again, I clearly don't see it here, so I'm rounding to the nearest thousand, 116,000 joules. Okay. 52. Which process represents one chemical change and one physical change? Now remember that physical changes only change the state of matter, like solid to gas, gas to liquid, yada, yada, yada. Chemical changes actually change what the substance is. You form new substances. So freezing and melting, both physical. Freezing and vaporization, both physical. Decomposition is a chemical change. Melting is a physical change. So this is what we want to go with. Remember, when something decomposes, it's breaking down into different substances. Choice D, decomposition and combustion. These are both chemical changes. So not that one either. All right, 53. A beaker with water and the surrounding air are all at 24 degrees Celsius. After ice cubes are placed in the water, heat is transferred from where to where? Okay. So a beaker with, sorry guys, my chair is moving. Bear with me. Okie dokes, gotta get myself comfortable. Okay, a beaker with water, again, sorry, I'm gonna repeat this. A beaker with water and the surrounding air are all at 24 degrees Celsius. So we got a cup of water, my beautiful water, okay. We place ice cubes in it. So we put some ice cubes in it. And then we wanna know what is happening to the heat. Obviously, the ice cubes are a lot colder. And remember that heat moves from high temperature to low temperature. So the heat from the water is going to move into the ice cubes and cause the ice cubes to do what? To melt. So we're going to go from heat is going to go from the water into the ice cubes. Choice C. Guys, I'm feeling a little energetic, so I'm going to attempt to do the next page as well. Let's see how far I can get. This question actually was on one of your labs. The freezing point of water, I believe, where we looked at the cooling curve of water. Okay. So a student obtained the following data while cooling a substance. The substance was originally in the liquid phase at a temperature below its boiling point. What is the freezing point of the substance? Now remember, they're asking at what point does this thing freeze? Freezing is a phase change. So during a phase change, the temperature is not going to do anything. So all you got to do is start looking for the values where they're constant for, a little bit of time. And I can see that right here. At minute 2.5 to about 4.5 minutes, the temperature does nothing. So that means that we are at this point on the graph. At this point, we are freezing, or really, it should be like this because it's a cooling curve. So we're at this point, and this is 53 degrees Celsius. All right. 55. The freezing point of bromine is what? Now, this you obviously don't know off the top of your head. Where do you go find it? You got to go to table S. So let's go take a look at table S for bromine. Let's flip this thing. So bromine is 35. Okay, and the melting point is this column. So melting point and freezing point happen at the same time. Okay, so it is 266 Kelvin. Okay, so 266 Kelvin, and let's go back. Problem is that all this stuff is in Celsius. So 266 Kelvin, we got to go to Celsius. To go to Celsius, you'd subtract 273. This is going to be -7 degrees Celsius. Again, freezing point and melting point are the same temperature. Okie dokes. I think there's like a lot of questions on this page though. Okay. Oh, good. Here is a vaporization question. So I'm just going to write over here. I got a little bit more room over here. How much energy is required to vaporize 10 grams of water at its boiling point? So this is Q equals M times HV. The value for vaporization is a lot higher. It takes a lot more energy or heat to boil water than it is to melt water, like ice, liquid, solid water. So we're looking for heat. We know that we've got 10 grams. HV is another physical constant of water. It is on your reference table. It is 2,260 joules for water. You multiply these and you should get 22,600, but they are reporting to kilojoules. This is in joules. So we have to convert from joules to kilojoules. All you got to do is just divide by 1,000. Okay, so you move your decimal 1, 2, 3 spots over. So it should be choice D, 22.6 kilojoules. 57, which equation represents sublimation? Sublimation is one of the phase changes that completely skips over the liquid phase. And again, remember my trick? Sublimation, so you start with S. You start from solid and then you go directly to liquid. So we just have to look for the equation that shows this change, and that would be choice A. Solid iodine subliming into gaseous iodine, okay? This is also an example of one of the things that sublimes. Solid iodine sublimes at room temperature. Solid carbon dioxide also sublimes. This is dry ice. Okay, usually if they're going to ask you a question about sublimation, they'll probably give you one of these two examples. And look at that. I literally just gave you the answer. So which species readily sublimes at room temperature? Solid carbon dioxide. Another answer that they usually give, again, is solid iodine. All right. No matter what the options for this were, you would have had to go with the thing that is a solid though, because only things that are solid can sublime. Look at that. I literally did not see this, you guys. Okay, which will sublime when heated? Iodine. Again, your two examples are carbon dioxide and iodine. Number 60, any substance composed of two or more elements that are chemically combined in a fixed proportion is a compound. Okay, compounds are in a fixed ratio, like H2O. The ratio of hydrogen to oxygen is 2 to 1. If I have something that is anything else, 3 hydrogens and 1 oxygen, or 2 hydrogens and 2 oxygens, the ratios are off. That means that they are not the same compound, okay? So a compound is always going to have a fixed amount of the atoms of their elements, all right? Okie dokes. So let's do number 61. Okay, I've actually given you guys this question before as well. Okay, so when sample X is passed through a filter paper, so we got filter paper or filter. Okay, so we put X through, and what happens is a little white residue called Y remains on the paper, and a clear liquid passes through, and we're going to call this Z. When liquid Z is then, we vaporize it, so that means that we put fire under it, another white residue remains. Okay, so that means that Z had a liquid and a solid in it, and that the solid was dissolved in Z. Okay, what this means, this is our example of sand, salt, and water. Okay, sand, salt, and water. So we had a heterogeneous mixture in the beginning. We had sand, salt, and water. That was sample X. We passed it through a filter. Okay, the sand was left on the filter paper, and the salt water came down, and then we boiled off the water, and we were left with the salt. So this is a heterogeneous mixture. Alrighty. All right, number 62, which represents a homogeneous mixture? A homogeneous mixture is also known as a solution. Things that are solutions are aqueous, mixed with water. So that is C. Number 63, describe diagrams X, Y, and Z. This was also a question on a lab, okay? This is a short response question, okay? So you can use multiple things to describe each of these. So X, this is showing two different atoms, and they are literally drawn next to each other. So this is representing a compound, and compounds are also considered pure substances. Okay, so that's how we can classify X. Y, I see that there are two things bonded to each other, but they are the same element. These are diatomic. So this is really an element. Okay, not a mixture of elements, but it's just an element. And it is also, elements are also pure substances. Z, again, I have diatomic elements. Okay, this is a mixture of elements. If something is a mixture, it's also not, it's not a pure substance. Okay. All right. That's all. Okay. Moving forward. Number 64. Which of these terms refers to matter that could be heterogeneous? The only thing that you can describe as heterogeneous is a mixture. The other type of mixture is homogeneous. Remember that heterogeneous is something that visually looks different. You can visually see the different parts of the mixture. Homogeneous means that it is evenly mixed throughout. Okay, something like salt water. The salt dissolves very nicely in the water. So when it's mixed together, you don't actually see the salt. Okay. Which sample of matter is classified as a solution? Again, a solution is a homogeneous mixture. This means that something has been mixed with water. This is something that is aqueous. So choice D. All right. Number 66, another question that I have given you guys before. If a student pours a mixture of sand and salt water through a filter paper into a beaker, what will be found in the beaker after filtering? So this was like 61. So after you pass it through, the sand gets trapped on the filter paper, and the only thing that comes out is the salt and the water. So this is choice C. All right. I'm just going to look at the next page, you guys, see what's going on. Yeah, I'm gonna stop here. All right. So wow, I covered a lot. 66 questions in one video. I really hope that this was helpful for you guys. I'm going to try and make some of the other videos, probably not today, but I will post this one for you guys. You can get started studying for your final. Again, first part of the final is 13th, and the second is the 19th. And if I use this video for next year, I don't know what the dates are. Okay, I'm doing this. This is 2023. So if you're listening to this in a different year, ignore this bit. All right. But anyways, guys, good luck. And I really hope that this was helpful. I'll see you guys in the next video.